To solve a system of two linear equations by the elimination method, we will first make sure that both equations are written in the form ax plus by equals c. Sometimes it's also necessary to multiply one or both equations by a constant so that terms containing the same variable have opposite coefficients. Then we can add the two equations together in order to eliminate one variable. Next, we'll be able to solve the resulting equation in order to find the value of the first variable in our system. And finally, we can substitute back into one of the original equations in order to find the value of the second variable. Let's look at the example shown on the slide. In this system, the first equation is 2x minus 3y equals 17, and the second equation is 4x plus 3y equals 7. Notice that both equations are already written in the correct form ax plus by equals c. And also notice that the coefficients of the y terms in these equations are opposites. In the first equation, the coefficient of y is negative 3. In the second equation, the coefficient of y is positive 3. This allows us to move to the third step of the elimination method, which is adding the two equations together. Now note that we can perform this step because of the addition property of equality. Essentially, we're adding the number 7 to both sides of the first equation. But on the right-hand side, we'll actually add the number 7. On the left-hand side, we'll add the equivalent expression, 4x plus 3y. And as we add those expressions on the left-hand side of this equation, we see that 2x plus 4x is 6x. And then negative 3y plus 3y is 0. The y terms cancel out because they have opposite coefficients. On the right-hand side, 17 plus 7 is 24. Now we can solve this new equation for x by dividing both sides by 6 to see that x equals 4. Knowing the value of x, we can substitute it back into either of the original equations in order to find the value of y. Let's use the second equation. So we have 4 times 4 plus 3y equals 7, or 16 plus 3y equals 7. Subtracting 16 on both sides, we obtain 3y equals negative 9. And finally, dividing both sides by 3, we have y equals negative 3. This means that the solution to our system is the ordered pair 4, negative 3. If we were to graph these two equations on a coordinate plane, we would see that we have intersecting lines at this point. Let's look at two more examples that are a bit more difficult. And again, we'll solve each system by elimination. Our first equation is 3x minus 5y equals 16. And the second equation is 6x plus 2y equals 8. Now both equations are written in the form ax plus by equals c. But if we examine the coefficients of x and the coefficients of y in these equations, we see that neither pair of coefficients is opposites. So in order to obtain opposite coefficients for one of our two variables, the simplest way to do that is to multiply the first equation by negative 2 on both sides. And we can see that if we do that, our first term will be negative 6x, which is the opposite coefficient to the first term in our second equation. So let's rewrite the first equation below the second one. We have negative 6x plus 10y equals negative 32. Now that the x terms have opposite coefficients, we can add the two equations together in order to eliminate those terms. So our new equation is 12y equals negative 24. We can now isolate y and see that y equals negative 2. And then finally, we can substitute back into one of the original equations to find the value of x. Let's use the second equation, 6x plus 2 times negative 2 equals 8, or 6x minus 4 equals 8. Add 4 to both sides, and divide both sides by 6 to obtain x equals 2. Thus, the solution to this system is the ordered pair 2, negative 2. Now our second problem, the first equation is 2x plus 3y equals 13. and the second is 5x plus 4y equals 15. Both equations are written in the form ax plus by equals c, but again, neither pair of variables have opposite coefficients. And in fact, in order to obtain opposite coefficients for a pair of variables in this system, we'll actually need to multiply both equations by a constant. Let's multiply the first equation in our system by 4, and the second equation by -3. Again, performing the multiplication on both sides to satisfy the multiplication property of equality. Now, why did I choose these particular numbers? Well, take a look at the y terms. When we multiply in the first equation, we'll have 12y, and when we multiply in the second equation, we'll have -12y. Other numbers besides 4 and -3 could have been chosen. For instance, if we wanted to eliminate the x terms, we could have multiplied the first equation by 5 to obtain 10x, and the second equation by -2 to obtain -10x. But let's proceed as has been shown on the slide and eliminate the y terms instead. Our first equation becomes 8x plus 12y equals 52. Our second equation becomes -15x minus 12y equals -45. And now we can add these two equations together. 8x plus -15x is -7x, and as expected, the y terms cancel out. Then on the right-hand side, we have 52 plus -45, which is +7. Thus, we can see that x equals -1, and we can go back to one of our original equations to find the value of y. Let's use the first equation from our original system. So we have 2 times -1 plus 3y equals 13, or -2 plus 3y equals 13. Adding 2 to both sides, dividing both sides by 3, we see that y equals 5. Thus, the solution to this system is the ordered pair -1, 5. Again, indicating that if we graphed these two lines on the coordinate plane, they would intersect at that point.